A look up at the night sky. It's a tapestry of stars, planets, and galaxies. Each point of light represents a distant sun, perhaps orbited by its own planets. The universe feels eternal, unchanging. But is it? This is a question humans have pondered since we first looked up at the cosmos. The universe, as vast and enduring as it seems, might have an end. Imagine a future where the universe is not as we know it. What if the stars themselves fade away? This is not a scene from science fiction, but a possibility pondered by scientists. Two leading theories, the Big Freeze and the Big Crunch, offer dramatically different endings to the universe's story. Both start with the same event though, the Big Bang. This image shows how the universe looks on a clear night sky. Billions of stars are present even in a tiny patch of sky. Let's explore these theories, diving into the science behind them and contemplating what each scenario means for the existence of everything we know. Our journey begins with a trip back in time to the very beginning of our universe. Imagine all of space and time compressed into a point smaller than an atom. This was the state of the universe roughly 13.8 billion years ago. Then, the Big Bang occurred. It wasn't an explosion in the traditional sense, but a rapid expansion. Space itself inflated, spreading energy and matter in all directions. From this primordial soup, the universe cooled. Elementary particles formed, eventually coalescing into atoms. Gravity drew these atoms together, forming the first stars and galaxies. The universe, once a uniform sea of energy, transformed into the structured cosmos we observe today. The image shows the widely accepted theory of the Big Bang. A small dot expanded rapidly to form the universe. Crucially, the Big Bang model tells us that the universe is still expanding. This expansion, however, might not continue forever. The fate of the universe hinges on a cosmic tug-of-war between the outward push of expansion and the inward pull of gravity. Let's delve into one possible outcome of this cosmic struggle: the Big Freeze. The Big Freeze, also known as the heat death, paints a picture of the universe's slow and inevitable decline. Imagine a universe where galaxies drift farther apart, stars exhaust their fuel, and the cosmos slowly fades to black. This chilling scenario is a consequence of the universe's continuous expansion. As the universe expands, the energy it contains, like the heat from the Big Bang, gets distributed over an ever-increasing volume. Think of heating a pot of soup. As you add more water, the soup cools down. Similarly, as the universe expands, its overall temperature drops, leading to a state of maximum entropy, where everything reaches a uniform low energy level. This image shows the expansion of the universe. Each stage of expansion has a lower temperature depicted with a different color. But the expansion alone doesn't tell the whole story. A mysterious force, known as dark energy, plays a significant role in accelerating this expansion and driving the universe towards its ultimate demise. In the late 1990s, astronomers made a startling discovery. The universe's expansion wasn't just continuing, it was speeding up. This unexpected acceleration pointed towards an unseen force counteracting gravity, which they dubbed dark energy. We know very little about dark energy, except that it makes up about 68% of the universe's total energy density. Its presence has profound implications for the Big Freeze scenario. As dark energy pushes galaxies apart at an increasing rate, the universe becomes a desolate and lonely place. This image shows the percentage of dark energy, dark matter, and normal matter in the universe. As the universe expands under the influence of dark energy, it becomes increasingly dilute. Stars will eventually burn out, galaxies will drift beyond our cosmic horizon, and the universe will become a cold, dark, and ultimately lifeless void. Stars in a dying universe. Stars are the cosmic engines that light up our universe. But even these brilliant giants have a finite lifespan. In a Big Freeze scenario, the demise of stars is inevitable. Stars like our Sun are powered by nuclear fusion, converting hydrogen into helium. But eventually, they run out of this fuel. As stars exhaust their fuel, they go through dramatic transformations, some ending as white dwarfs, neutron stars, or black holes. In the Big Freeze, these remnants will fade into darkness. No new stars will form to replace them. Section 6. The universe fights back. Gravity's final stand. We've explored the chilling consequences of a universe dominated by expansion and dark energy. But what if another force challenges this fate? What if gravity, the architect of stars and galaxies, stages a comeback? The Big Crunch theory proposes an alternative ending to the universe's story. In this scenario, gravity eventually overpowers the expansion. The universe's expansion slows down, halts, and then reverses. Instead of drifting apart, galaxies begin rushing towards each other, setting the stage for a cosmic catastrophe. This image shows the Big Crunch theory, where the universe contracts to a single point. Imagine the universe as a ball thrown upwards. Initially, it ascends with great speed, but gravity gradually slows it down. Eventually, the ball stops and falls back to the ground. Similarly, the Big Crunch envisions a universe where gravity eventually reverses the expansion, pulling everything back to where it all began. Section 7. The Big Crunch, a universe collapsing on itself. As gravity takes over, the universe undergoes a dramatic transformation. Galaxies, once separated by vast distances, begin to collide, triggering intense bursts of star formation. The sky, once a serene expanse, becomes a chaotic kaleidoscope of merging galaxies and exploding stars. As the universe contracts, the cosmic background radiation, the faint afterglow of the Big Bang, heats up. Temperatures across the universe rise dramatically, making the universe an inferno. Planets are vaporized, stars are ripped apart, and even black holes are consumed in this cosmic maelstrom. This image shows two galaxies colliding with each other during the Big Crunch. The Big Crunch culminates in a singularity, an infinitely dense and hot point where the laws of physics as we know them break down. This singularity mirrors the one from which the universe originated, potentially offering a chance for a new beginning. Section 8. Fire and Fury, the universe's climactic end. The final moments of a Big Crunch universe are a dramatic departure from the slow fade of the Big Freeze. As the universe shrinks to an infinitesimally small point, temperatures and densities reach unimaginable levels. The very fabric of space-time is torn apart. Imagine a furnace hotter than any star, where matter itself is crushed into oblivion. This is the unimaginable environment of the Big Crunch. Black holes, once the universe's ultimate devourers, merge and grow, eventually consuming everything in their path. This image shows the universe with high density and temperature. This fiery end, while cataclysmic, is not necessarily the final word in the universe's story. Some physicists believe that the Big Crunch could be followed by another Big Bang, creating a cyclic model of cosmic evolution. Section 9. From the Ashes, the Cyclic Universe. The idea of a cyclic universe where Big Bangs and Big Crunches alternate in an endless dance of creation and destruction is a captivating one. This model suggests that our universe is just one chapter in an infinite cycle of cosmic evolution. Imagine a phoenix rising from its own ashes. In the cyclic model, the Big Crunch singularity, instead of marking the end, becomes the seed for a new Big Bang. The universe is reborn, expanding outward before gravity pulls it back together, repeating the cycle. This image shows the cyclic model of the universe, where the universe expands and then contracts. While the cyclic model is highly speculative, it offers a fascinating perspective on the nature of time and existence. It suggests that the universe is not a finite entity with a defined beginning and end, but rather an eternal, self-renewing entity. Section 10. Our fleeting moment in cosmic history. Whether the universe ends in a whimper or a bang, one thing remains certain: our time within it is finite. The vast scales of cosmic time dwarf the entirety of human history. Against the backdrop of an evolving universe, our existence is but a fleeting moment. The contemplation of the universe's end can feel daunting, even unsettling. It reminds us of the impermanence of everything we know and love. Yet it also highlights the preciousness of our present moment. This image shows Earth from space. Earth looks very small against the background of billions of stars. We are fortunate to live in an era where we can ask these profound questions about the universe's fate. We can marvel at the intricate workings of stars and galaxies and ponder our place within this grand cosmic scheme. Section 11. Embrace the present, under a timeless sky. So, the next time you find yourself under a starlit sky, take a moment to appreciate the vastness and mystery of the universe. Remember that the cosmos is in a constant state of flux, evolving over timescales that dwarf our existence. Let the contemplation of the universe's end inspire you to live in the present moment, to cherish the time you have with loved ones, and to contribute to the tapestry of human knowledge and experience. For in the grand scheme of the cosmos, our lives may be fleeting, but our impact on the universe, however small, is a part of its ongoing story. As we continue to explore the universe and unravel its mysteries, we gain a deeper appreciation for the delicate balance of forces that shape our existence. The end of the universe, whether a big freeze or a big crunch, is a reminder of the interconnectedness of everything in the cosmos and the profound beauty of the natural world.